Hi, ladies and gentlemen. Welcome to Soil Mechanics online course. I'm Rui Chen, Associate Professor from School of Highway, Chang'an University. In this course, I and my colleagues will introduce you the basic concepts and fundamental principles of soil mechanics. Before walking you into the main content, I would like to do a brief introduction about this course and answer the questions you may have. The first question you may have is, what is soil in the eyes of civil engineer? Soils are natural resources. They provide us food, shelter, and construction materials. Soil has many different meanings depending on the field of study. In this course, we will consider soils as construction materials and as support for structures constructed on or within them. Technically, soil is defined as the uncemented or weakly cemented aggregate of mineral grains formed by weathering of rocks, the void space between the grain containing water and or air. This definition tells you two pieces of information. First, soils are weathering product of rock. And second, soil is a three-phase material, which consists of solid particles, air, and water. Especially the presence of water makes the behavior of soil extremely complex and hard to predict. For example, dry sand can float like liquid, but you can make sand castles from damp sand. Dry clay can be as hard as rock, but wet clay can be squeezed and molded like peanut butter. The second question you may have is, what is soil mechanics about? Well, let's first talk about the history of soil mechanics before answering that question. From 1920s, the fast growth of cities and industry demands complex building systems. For instance, skyscraper, highways, airports, etc. These building systems require stable and economic foundations. In dealing with soil engineering problem, we need the help of a theoretical framework, and consequently, soil mechanics was born. Soil mechanics is defined as the application of engineering mechanics and hydraulics to the solution of problems dealing with soil as a foundation and a construction material. Carl Terzaghi is the undisputed father of soil mechanics. He made significant contributions on many topics, especially consolidation theory, principle of effective stress, foundation design and construction, and landslide mechanisms. In particular, soil mechanics deals with three major topics: shear strength of soil, deformation of soils, and seepage through soils. Example related to shear strength of soils is landslide. Although the landslide mechanisms are rather complex, it is commonly accepted that the gravity and seepage forces induce shear stress in the soil mass. If this induced shear stress is greater than the shear strength of soil, then shear failure may occur. If the shear failure dominates large area in the soil slope, then landslide may happen. As you can see from this picture, landslide can cause significant property loss and even lives. Another example related to shear strength of soils is liquefaction. The picture shows building collapsed in the 1964 Niigata earthquake in Japan. As you can see that the upper structure of the building was still intact, but due to liquefaction, the foundation soil lost its bearing capacity, leading to collapse of the building. When earthquake hits, the pore water pressure within the saturated soil builds up so rapidly, leading to full loss of shear strength. Soil particles are floating in water, behaving like liquid. This phenomenon is called liquefaction. After learning soil mechanics, you may better understand this phenomenon using the principle of effective stress. Classic examples related to deformation of soil are Leaning Tower of Pisa in Italy and a deformed building in Mexico City, as shown in the slides. The common point of these two structures is that they were built upon a thick layer of soft clay. The soft clay is highly compressible and has caused damaging differential settlements in the structures. After learning the consolidation theory in soil mechanics, you can have a better understanding about settlements of structure built on clay. A classic example related to seepage through soil is the failure of Teton Dam. Construction on the Teton Dam began in 1972 and completed in 1975. Less than a year later, the dam experienced catastrophic failure on June 5, 1976, during its first filling. Failure of the Teton Dam caused the deaths of 14 people, and the subsequent cleanup cost approximately $2 billion. The failure of Teton Dam was caused by internal erosion initiated by hydraulic friction of the fill material. Internal erosion progressed rapidly through the body of the dam, leading to seepage failure of soil and finally complete failure of the dam. Next, I would like to talk about the features of this course. First, in soil mechanics, many simplifying assumptions regarding the mechanical and hydraulic property of the soils were made. However, when properly applied, the results obtained by means of these approximate procedures are accurate enough for most practical purposes. Second, in dealing with soil problems in engineering practice, field observation and engineering judgment are as important as fundamentals of soil mechanics. Soil mechanics may provide a solution to a mathematical model. Due to the complex nature of soil, and our knowledge of subsoil condition is always incomplete, the math model may be far from the truth. As construction proceeds, soil behavior should be observed, and the design may subsequently have to be modified in accordance with the findings. The basic concepts and fundamental principles of soil mechanics will be covered in 8 chapters. We recommend 2 textbooks: Principles of Geotechnical Engineering by Dr. Das and Soil Mechanics and Foundations by Dr. Boodoo. Please join me on a journey of learning soil mechanics, and I hope you enjoyed it and get something useful. That is all for today. Thank you for your attention. See you next time.